Okay, so now we're going to start looking at the reactions between acids and bases. So again, this unit is all about reactions in solution, or aqueous reactions. So acid-base reactions would be an example of that. In grade 10, we learned about the pH scale. We learned about what an acid-base reaction is, that acid and base react to produce salt and water. And we kind of started talking about like some simple definitions for acids and simple definitions for bases. And we're going to take that a little bit further in the grade 12 course. So first things first, some quick review from grade 10. From grade 10, we learned about the properties of acids and the properties of bases. So some things that we talk about are things like acids, actually we'll put acids in red, acids taste sour. They turn blue litmus to red. I've heard some people remember it with that word, bra. Blue turns red in acid. That might help you. They neutralize bases. They are corrosive. In other words, they react with metals. They are electrolytes. And they burn your skin. Now, if we're talking about bases, bases are kind of, you think of bases as the opposite of acids. So if acids taste sour, I guess some people would say sweet is the opposite of sour, but bitter is what we're looking for. So if you've ever gotten soap in your mouth, you would know that bitter taste. That's from a base. Bases also feel slippery. That's why soap feels slippery. They turn red litmus blue. They neutralize acids. And they are electrolytes. In other words, they form ions. And they are caustic. That means they dissolve organic material. So corrosive reacts with metals. Caustic breaks down organic materials. In fact, bases are actually used to make pulp from wood for paper production. Breaks down all the organics in the wood to make it into a pulp that we can press out into paper. So if you're looking at what acids have, acids will have lots and lots of H's and very few OH's, and bases will have lots of OH's and very few H's. So since acids really have H pluses and bases really have OH minuses, if you put these together, we get H2O, which is water. So that's basically neutralization. And that's what I said earlier. Acids neutralize bases, bases neutralize acids. And why? Well, because H's and OH's get together and form waters, which is neutral. We'll talk about pH. I guess if we wanted to add in a pH, that's probably something good to put in here too. So pH of an acid is less than 7, and pH of a base is greater than 7. pH of 7 exactly is perfectly neutral. So acids are less than 7, bases are above 7. Okay, so there's some common acids and bases that we should know. Now, you do have an acid strength chart that you will get to use. I'm just going to put these up here. And they are all on there. So really, at the end of the day, we don't have to memorize the names of these acids. There's actually also a system for naming acids that if you want to search out online, you can find it. It's got to do with our chlorates, chlorites, hypochlorites, and the way we change our prefixes and suffixes. We don't actually need to learn it in this course, but it's something that you will probably come across down the road. The other thing, one other thing about acetic acid, you might also see acetic acid written like this, HC2H3O2. If you remember from grade 11, if we got to the organic chemistry unit, this COOH tells us that it's a carboxylic acid. So that actually tells me that that looks like this, tells me the structure. But lots of chemists will just write acetic acid like so, hydrogen acetate, same idea. And it's the hydrogen ion and an acetate ion, same thing. And if you're wondering what is acetic acid, it's vinegar. Not that you have to memorize that, but just something interesting since it's something we're familiar with. Bases, now most bases are hydroxides. We'll see a lot that aren't later. The main one that I'd like you to remember, and unfortunately this one we just kind of have to memorize, is ammonia. it is a base. And its formula is NH3. And it's kind of one of the weird ones. Like if you think about acids, they all seem to have H's at the start. And bases all seem to have OHs at the end, with the exception of ammonia. And if you ask most grade 9 or 10s and said, hey, which is that? Is that an acid or a base? They would probably say it's an acid because it has H's. But actually, ammonia does a weird thing when it goes into water, and it makes OH ions. So it's actually a base. It acts more like a base. Now, we'll get more into the properties and the reactions of the acids and bases when we get to that actual unit. But for right now, these are just kind of some common acids and bases that we should be aware of. Right. So for right now, this is the definition that you guys were taught in grade 10, is that acids basically release H ions and bases basically release OH ions. So acids have H's, bases have OHs. And together, H's and OHs make water. So you can think of it basically as we're just dissociating the acid or the base. So if you have some H something, that becomes H ions and something ions. If you have NaOH, you get Na plus ions and OH minus ions. So now this actually will explain why ammonia produces OH ions in water, but we have to include water as part of the reaction. Ammonia actually steals an H from water, and it becomes ammonium and then hydroxide. So this is a weird way of ionizing. It actually led to another definition of acids and bases that we'll talk about later in the course. But basically what I'm trying to get at is if these make H's and these make OH's, together when we mix them, we're likely to get H2O. And remember, H2O is a pH of 7, which is neutral. So that would be what we call a neutralization reaction. So from grade 10, neutralization reactions are really just double replacement reactions or double displacement reactions, however you want to say it, between an acid and base, and they produce salt and water. Now, when I say salt, I'm not talking about table salt. Everybody thinks that NaCl is salt. It is a type of salt. Basically, a salt is an ionic compound. That's pretty much anything that's an ionic compound, metals and nonmetals, you can call it a salt. That's the technical term for metals and nonmetals in chemistry. We are just familiar with a specific type of salt called table salt, known as sodium chloride. Now, going back to acids and bases, remember that they're basically the opposites. But when you have them in equal proportion, they're going to combine to form water, which is neutral. Now, what we're trying to say is if the moles of H's, the moles of H plus ions, and the moles of OH minus ions are equal, we get a pH of 7, which is neutral. And we'll explain what the pH scale means a lot more down the road. So what we can do, and I guess the last thing I should probably say here is that the resulting solution will conduct electricity, which means there's ions still present, and we'll get to that in a second. So what we can do is we can take these reactions. So here's the stereotypical acid-base reaction. You have HCl and NaOH making actual table salt and water. This is kind of the simplest acid-base reaction we could write. Now, what we can do is we can take these and break it down into molecular, ionic, and net ionic equations, just like we did with our precipitation reactions. You could actually think of this reaction as a precipitation reaction because water is coming out of the solution, so to speak. We are making a pure substance from two aqueous solutions. Now, the water just adds to the mixture. It's just part of the whole mixture, but you are making more water when you react the acid and the base. So what we can do is write those three types of reactions that we've been doing. And this is what it would look like. So our molecular reaction will just be your typical reaction that we would write, the double displacement neutralization reaction. NaOH and HCl makes NaCl and H2O. But our total ionic is where anything that is an aqueous ionic solution is dissociated. So that means that this, and this are all able to be dissociated. But because H2O is a pure substance, it's not dissociated. It's not in solution and it's not broken up. So you can think of this as a water precipitation reaction. And this is what you would get. Now, going back and putting my arrows or my square brackets in just to kind of organize the data a little bit better. Kind of looks like this. To me, that just kind of, I can see what's what a little bit better. But looking at this, what you see is the sodiums cancel and the chlorides cancel. So we've gotten rid of our spectator ions, and what's left is H plus and OH minus making H2O. So our net ionic equation is just that. H plus plus OH minus makes H2O. And this is your net reaction. And actually, all acid-base reactions should have this as their net. One H and one OH makes H2O. Now, there's an example for you to try. This is a little bit more practice with our molecular ionic and net ionic equations, but see if you could write the molecular ionic net ionic equations for the reaction between potassium hydroxide and sulfuric acid. Pause the video, give it a shot, and see if your answer matches mine in a minute. So I'm going to write my KOH plus H2SO4, and we're going to make, so K goes with SO4, that'll be K2SO4, and H2O. And now we'll have to go back and balance this. So I've got 2 potassiums there, so I need to put a 2 here. And now that means on the reactant side I have 4 hydrogens, so if I put a 2 there, that gets me my 4 hydrogens, and my oxygens are balanced, and so are my sulfates. Now I'm going to put in my states. This is aqueous, aqueous. K2SO4 would be aqueous, AQ. And H2O is going to be a liquid. All right, so now going through anything that is ionic and aqueous, we can dissociate. So KOH is going to make K plus and OH minus. But there are 2 KOHs, so I'm going to make 2 Ks and 2 OH minuses, and they're both going to be aqueous. Now I'm going to add in my square brackets. All right, next one. Might as well put a square bracket there. H2SO4 is going to make Get rid of that. It's going to make H plus and SO4 2 minus. But because there are 2 H's in H2SO4, I'm going to get 2 there. These are aqueous as well. On the other side, K2SO4 is going to make K plus and SO4 2 minus, but to keep it balanced, there needs to be 2 Ks. Again, aqueous, aqueous, brackets here. And my last product is H2O, which is a liquid, but there are 2 of them because it still has to be balanced. Now, looking at the reaction, I can go through and cancel my spectator ions, Ks, SO4s, and I'm left with this. 2H plus plus 2OH minus makes 2H2O. And these are AQ, AQ, AQ. Now, if we think about this reaction, we got 2 and 2 and 2. The reaction is 2 to 2 to 2 ratios. Well, we can reduce those ratios. So anytime we can reduce our coefficients in a reaction, we will. We want the lowest whole number ratio for our reactions. So the net reaction will actually be H plus aqueous plus, I'm just going to change that to an O. OH minus aqueous making H2O aqueous. Or not aqueous, I should have that as a liquid. My bad. That should be a liquid. So there's our net reaction, and if you look, it's actually the exact same net reaction we had in the previous example. So it doesn't matter which acid or base you react, the net reaction of a neutralization reaction will always be H and OH makes H2O.